All right, we're working on 2012, question 1 for your response. All right. Now, for this first part, it says determine the equation of VT, including numerical constants. So, uh, you don't have to do calculus for this, even though normally when you're looking for something like this, V isn't a function of T. It usually means calculus, but in this case, it's basically come up with the equation based off of this graph. Now, if you look on the reference table, or you remember from when we talked about it in class, the equation for any harmonic motion is basically, oh, I'll erase that, is Vmax times sine or cosine omega t. That's the basic equation. And recall that omega, the angular frequency, is just 2 pi times the frequency. Alright, so let's see. In this case, and this is true for all the equations, for position and for acceleration. The only difference would be instead of being a sine, it would be a cosine. Alright, so first off, I know that it reaches a maximum value of, let's see, I'm eyeballing it right now. I'm going to say 0.16. 2, 4, yeah, I'll go with that. 0.16. That's what my Vmax is going to be. My frequency is cycles over seconds. So that's going to be, let's see, I get one full cycle there, and that's 0.5, 0.6, 0.7. So one cycle in 0.7 seconds. And that gives me a frequency of 1.43. Which means my angular frequency is going to be 8.98, or you could even round it to just being 9. Alright, so that means that my equation is going to be V of t equals 0.16 sine of 9t. Now, one thing that you have to be very careful about is this, because this isn't completely, it isn't complete. Because if you notice, this graph goes negative first. So it's not a sine graph, it's a negative sine graph. Alright, so this is the full equation. Negative 0.16 sine 9t. Alright, now this was a whopping 4 points. There was 1 point for getting this equation with the negative. You had 1 point for realizing that it's going to look like this. You got 1 point for figuring out 1 point for realizing that that was the frequency, the equation. Got 1 point for determining the proper frequency. And that was basically it. Yep. So that's, yeah. They did say that they would give you partial credit if you used an answer for part C to calculate omega. But like I said, this is how you get your full 4 points. Alright, now it's asking for us to determine the equation x of t using numerical values. Alright, so this is, for the most part, this is calling for us to use calculus. However, you don't have to use calculus if you remember what the graph should look like. I said before that the way these graphs are, they should be shifted. So if our velocity graph looks like this, then our position graph originally looked like this. So if velocity is a negative sign, then position should be a positive cosine. And likewise. Or you could use conceptual, saying, oh, based off of this scenario, it must start off in the positive direction and then go to negative. So it should look like a cosine curve. So you could use that to come up with your answer, realizing that, it should still follow the same thing. X of t equals x max cosine of omega t. And remember, this number should still be the same, so you end up getting, let's see, do they tell us what the maximum position is? No, but what you can do is use the velocity, the max velocity, to determine max position by using conservation of energy. So we have 1/2 k x squared equals 1/2 mv squared. And that's m over k. And you end up getting, instead of 0.16, square root of 0.3 divided by k. Oh, we don't know what k is? Alright, let me just get rid of this. Now you can find a way to find k, and you can work on it by using fx equals kx, plugging that in for k. But instead, I'm going to actually just take the calculus route. Alright, so remember that position is just the integral of velocity with respect to time. So it was negative 0.16, integral of negative 0.16, sine of 9t dt. This requires you to kind of remember or know how to do integrals with trig functions, something you juniors unfortunately don't know, but it's not that tricky. So what you do is pretty much similar to what you would think. The sine becomes a cosine. In fact, this integral is actually on the reference table. You look at it, you see the integral of sine x dx equals negative cosine x. So what that's going to do, this negative 0.16 is a constant value. So that gets pulled out of the integral. And then you take the integral of this, so you end up getting negative cosine 9 of t. But you have to take into account that 9 in there, so that gets divided by with this. So this ends up being your integral. Negative cosine 9 over 9t divided by 9. Alright? So this negative cancels out with that negative. The 0.16 divides with the 9 to get us 0.01 e cosine 9 of t. And this is what you end up getting for your answer. Alright? Now, I should have been... now, like I said, there was a way to actually come up with this without having to do integration. And I started showing you how to do it. It was, I was right, you do the whole potential equal to kinetic. You get that x squared equals v squared square root, x equals v times rad m over k, which is just x equals v divided by omega. Because if you remember, on the reference table, you know that the omega for a spring is rad k over m. So rad m over k is just 1 over this. Yep, didn't mean to write that. Alright, so if you just did the maximum velocity divided by the angular frequency that we got before, then you would have gotten 0.018. Alright, so you didn't have to actually do the calculus, but that was probably the most quickest way. Now, you would have gotten 1 point for basically realizing that your answer should be cosine. So 1 point there or here for realizing that it's cosine. And then you got 1 point for getting this proper position. Now, the good thing is that for this was 2 points, but for this, it all had to be consistent with your previous answer. So if you said your answer was cosine from part A, like you said that for some reason you said the velocity was a cosine graph, then your position graph should look like a sine graph. You know, stuff like that. So this is all these answers are based off of the previous part. Alright, for this, there's 2 different ways to go about doing it. One of them is to use the equation, the period equals 2 pi rad m over k, and solve for k. Or, since we already have it, omega equals rad k over m. Move some things around, and you get that k is going to be equal to omega squared m. Omega, if you remember, was 9. Mass is 0.3. So this ends up being 81 times 0.3. So k will equal 81 times 0.3, 24.3. And this one was a simple 2 points. 1 point for basically coming up with either of these equations, and 1 point for substituting in the parts from your previous answers correctly to get an answer. Alright? Easy peasy. Alright, now we have to do an FBD of the block when the spring's compressed and when the block is moving in the direction indicated by each block, and it's got a rough surface. Alright, so one thing is that there should be we know that there's automatically 2 forces acting on this, Fn and Fg. And I know my lines aren't really proper, but they should be equal in size and equal to each other. So Fn here should be equal to Fn here, and the Fg here should be equal to this Fg. Alright? Now we have to think about the spring force. So let's see. When it's moving toward the equilibrium position, that must mean when it's here. That's one thing to remember. So the spring's compressed, and this is the equilibrium position. So in the first part where it's moving toward the equilibrium position, then the spring is pushing it to the right. Because that would be towards the equilibrium position. But if it was moving away from the equilibrium, then the force is still going to be pushing it to the right. Because remember, the spring force always pushes it towards the equilibrium. So if, no matter where this or how this object's moving, if it's to the left of the equilibrium position, then the spring force will always be to the right. All right. So that was easy, but now we have to take into account friction. So let's look at this. It's moving toward the equilibrium position, so it's moving to the right, which means friction has to oppose it. So friction has to move to the left. Now when it's moving away from the equilibrium position, again it has to oppose that motion, so it's moving to the left. Now friction is going to be moving to the right. So this is what your FBD should look like. Both ones should have 4 forces. Here, the 4 forces are in opposite directions. Here, 2 of the forces are in the same direction. Spring and friction. Now, this was 4 points altogether. You got 1 point for correctly doing Fn and Fg for both. You got 1 point on this diagram. Let's see. You got 1 point for realizing that friction is going in that direction, and 1 point for realizing spring forces in that direction. And then you got 1 point for basically realizing these two are in the same direction to the right. They did say that in here, the length of the vectors does not really matter. So unlike the AP1, where a lot of times you do have to make sure you take into account the length, here, not so much. And they said that 1 point was deducted if you added extra forces or if the vectors weren't touching the object. So that means that you cannot do an FBD like this. The force has to be touching and originating from the object, which means that it also can't do this. So just keep that in mind. It has to start on the point and then continue forward. Alright. Now they want to draw a sketch of velocity versus time in the case and assume that there is a negligible change in the period and that positive direction is still to the right. Alright, so let's see, the period from before was still 0.7. So let's keep that in mind. So 0.7. And I'm going to assume it starts off, this says positive is to the right. Since this block is displaced here, and with I think it's supposed to be moving towards the equilibrium, this object is going to initially go to the right. And let's see, remember it was towards, the 2 forces were in opposite directions, and away, the 2 forces were in the same direction. Alright, so it doesn't matter which side of the equilibrium point it's on, that's pretty much always going to be true. When it's moving towards it, the 2 forces are in opposite directions, and when it's moving away, then the 2 forces are moving in the same direction. Now, if you remember, the other thing is that when we have friction, it's not going to go nearly as far. So if it starts at amplitude A here, it's going to reach some position less than A. And then it's going to reach over here, and over here, and over here. So the amplitude of the graph should end up decreasing for both the position, the acceleration, and even the velocity. So the max velocity doesn't really matter. So let's say that it reaches the maximum right here. So the graph's gonna, okay, let me actually get my bearings. 1, 2, 3, that's halfway. Alright, so it's gonna go up like this, but here it's probably only gonna reach over here now. So then it's gonna go to here, and then here it's gonna reach maybe halfway again. So 1, 2, 3.5. And then maybe it's going to reach a little bit less. See, this is where the max is. 1, 2. I think I did my counting wrong. Yep, definitely did my counting wrong. Oh, can't redraw it. Because this is where 0.7 is. Which means 1, 2, 3. So ignore the black line. It should be 1, 2, 3. I know it's a little hard to see what's going on. And you end up getting something that looks something like this. Alright? So you get 1 point for basically realizing that the period should still be the same, that it should end up making one complete cycle every 0.7 seconds. You get 1 point for realizing that the graph starts at 0 and then goes initially positive. And then 1 point for realizing that the oscillation is damped. So I definitely made this comment before in class, but a damped oscillation means that there's friction and that the amplitudes are constantly decreasing. So again, here you can see that the amplitude keeps on decreasing each and every time, slowly going to 0. So this is where you get your 3 points. Realizing it goes 0 to positive, period stays the same, and damped oscillations. All right. So go over this. If you have any questions, let me know as soon as possible.